In this video, we're going to learn about continuity. Now, continuity is a pretty easy idea in general. If you're looking at a graph, just imagine, as a rough rule, if you can draw on the graph without picking up your pencil, the function is continuous. So you could have some crazy curve that looks like this. It winds around and around and around, but you never have to pick up your pen to draw it. That's continuous. Now if you have something that looks like this, this would be discontinuous. You see there's a jump, there's a break in the graph. These lines don't match up. If I was drawing this, I come in here, and then I'd have to pick up my pencil and move it down here to continue drawing it. Another example is the graph of y equals 1 over x. That looks like this, right? This is also not continuous. To get from here to here, I had to pick up my pencil. That's the basic idea of continuity. So now let's get into the mathematical definition. So let's say we have a function y equals f of x. A function y equals f of x is continuous at a point x equals c if now there are three different requirements for continuity, okay? The first one is easy. It's just that f of c exists. That means that the value of the function has to exist. The second is the limit as x approaches c of f of x exists. Right? And the third is the limit as x approaches c of f of x is equal to the function at that point. Okay, so this can be confusing at first. So let's look at three examples. Here's example 1. Let's say we have the graph y equals x squared. Okay, we know that looks like this. And what do you think? Do you think this is continuous or not continuous? Think about if you had a pencil and you were drawing this. It doesn't seem like there's any points where we'd have to lift up the pencil. There's no breaks. So we think it would be continuous. Let's check it with the definition, see if these three different things hold, okay? So the first check. We need to check to see if f of c exists. Well, c can be anything. Let's check a specific point. Let's just check x equals 0 here. So does f of 0 exist? Does x squared evaluated at 0 exist? Yes. F of 0, that's just 0 squared, which is 0. That exists. So we're well on our way to showing that this is continuous at the point x equals 0. The second check, the limit as x approaches 0 of x squared exists. Let's take a look at the right hand and left hand limits. As x comes in towards 0 from the right, the function approaches 0, and same from the left. The left and the right hand limits equal 0. That means that the limit as x approaches 0 of f of x exists. Okay, so the second condition is met. Now for the third condition, the limit as x approaches 0 of f of x, that has to equal f of c. Well, we showed that f of c was 0 in the first part, and we know that this limit equals 0. So since this limit equals 0, and that equals f of 0, all three conditions are met. This function is continuous at 0. It's actually continuous everywhere. Let's do another example. For example 2, we're going to look at this graph. Okay, so at x equals 0, I'm filling in this circle. So f of 0 is 1. Okay, let's check each condition. First condition, I just told you that f of 0 is 1, so f of 0 exists. That's pretty easy. Let's go on to the second condition. Does the limit as x approaches 0 of this function exist? Well, the limit from the right would be equal to 1, but the limit from the left is equal to -1. The left and the right hand limits are not equal. That means that the limit as x approaches 0 of f of x does not exist. DNE does not exist. Because of that, this function is not continuous. And that makes sense, right? If you were trying to draw this, you came in from the left here, you would have to pick up your pencil to continue drawing it. There's a break in the graph. Okay? And now for our final example. Let's look at this graph. This one's going to essentially be y equals x, but I'm going to make a little hole there, and I'm going to fill in y of 0 as 1. Okay? So this is f of x. Let's check the conditions. Well, f of 0 is 1, just like I told you. How about the limit as x approaches 0? Well, from the left, as we come in, we get closer and closer to 0. So the left-hand limit is 0. And from the right, we also get closer and closer to 0. So the left and the right-hand limits equal each other. They're both equal to 0. That means that the total limit as x approaches 0 is equal to 0. So the first two conditions are met. How about the third, though? Now we need to check to see if the limit as x approaches 0 of f of x is equal to f of 0. Well, the limit as x approaches 0 of f of x is equal to 0. However, f of 0 is equal to 1. So this is not equal to 1. The limit as x approaches 0 is not equal to the function value at 0. That makes sense, right? On either side, the line is getting closer and closer to 0, but you have to actually jump up to 1 at 0 to fill in f of 0. And that makes sense that this is not continuous, because you couldn't draw this without lifting up your pen and filling in 1 right here. So this is discontinuous. So that's a little introduction to continuity. I hope it made sense. If you're confused, just keep thinking about drawing the lines and if you have to raise your pencil or not.